Welcome back to Math 156, Algebra and Trigonometry for Calculus. Today we're going to be talking about ellipses. An ellipse is defined by two fixed points, here labeled F1 and F2, that are known as the foci, singular form, focus. And the ellipse is the set of all points P. Here's one of the points P, here's another point P, here's another point P, all the way around this ellipse. Those points are defined such that the distance from F sub 1 to P plus the distance from P to F sub 2 is the same for each of these points. Although the individual lengths differ when you add them together, the sum is the same. You can also draw a line segment that connects F1 and F2, the two foci, and the midpoint of that line is the center of the ellipse. Now, neither the foci nor the center are part of the ellipse. All the points P around in what looks like an oval, the ellipse, that is considered the ellipse, but the center and the foci are very important in graphing an ellipse. Now, an ellipse can be oriented in any direction, but most commonly we'll look at them horizontally and vertically. So let's make this ellipse a little bit smaller so I can show you two more important lines that we can draw on it. So if we extend the line that goes through the foci and the center, we are drawing the major axis. And the endpoints of that major axis are known as the vertices, or singularly, each is called a vertex. So one here and one here. If we now draw a line perpendicular to the major axis that goes through the center and touches the ellipse on either side, we have drawn the minor axis. And we have two endpoints of the minor axis. They don't get a special name, they're just the endpoints. But now we're going to take a look at ellipses on Cartesian planes. So here we have an ellipse which is centered on the origin. So in fact, the coordinates of the origin are 0, 0. And then we have one focus over here, and we could call that C, 0. It's over there on the x-axis, some distance c, and over here is the other focus at negative c. We could call the intersection of that major axis, because it's the longest one, that vertex A0, and this vertex negative A0. Why? Because that's what we've chosen to call it. Now, the endpoints of the minor axis are located on the y-axis of our coordinate plane, and so the x values for each of these will be 0, and we'll call the y value b. And if we orient this ellipse, and name those using those conventions, we can write the equation of this ellipse. And the equation for this ellipse would be x squared plus y squared, but it will be divided by, in this case, our major axis is along the x-axis, and each of those vertices is located at a distance a from the center. So we have x squared over a squared plus y squared over b squared, and that is equal to 1. So that is the standard form of the equation of an ellipse whose major axis is along the x-axis and whose center is at 0, 0. Let's compare this with an ellipse whose major axis is along the y-axis of our Cartesian plane. Its center is at 0, 0. To indicate which of the axes is the major axis, we will use A to indicate the distance from the center to the vertices. So the vertices are at points 0A and 0, negative A on our y-axis. And that means the endpoints of our minor axis will be B, 0, and negative B, 0. And at this point, before we name the foci, we can actually write the standard form of the equation of this ellipse. It will be x squared, but remember now the x-axis is the minor axis here. So it has b squared underneath it, and the y squared has the denominator, a squared, for the major axis. And then we can denote our foci as being at 0, c along that major axis, and 0, negative c. Yes, there is symmetry over the x-axis and over the y-axis in any ellipse. Now, for either of these ellipses, whether you have one whose major axis is along the x-axis or one whose major axis is along the y-axis of the Cartesian plane, it is true that the distance to either of the foci squared is equivalent to the distance from the origin to the vertices squared minus the distance from the origin to the endpoints of the minor axis squared. Be careful, it looks similar to the Pythagorean theorem, but it is not. So I'm going to make all of this a little bit smaller so you can still kind of see it. And we're going to put this together. All right, here we have an equation. It is clearly not a linear equation. We have an x squared and a y squared, but neither does it look like our standard form for an ellipse. We need to have a 1 on the right side and everything else on the left. Well, we can accomplish that by dividing both sides by 144, which means you have to divide each term of the left-hand side by 144. And then we can reduce. 16 goes into 16 one time and into 144 9 times. 9 goes into 9 once and into 144 16 times. And then, of course, the right-hand side will reduce to 1 over 1, or just 1. Since y squared has the larger denominator, we have an ellipse whose major axis is along the y-axis of the Cartesian plane. Therefore, a squared equals 16 and a equals 4. So we can draw our vertices of the ellipse at 0, 4 and 0, negative 4. Our smaller denominator is 9, so it gives us the coordinates of the minor axis, because b squared equals 9, so b equals 3, and our endpoints of the minor axis are located at 3, 0 and negative 3, 0. We have found our vertices, we have found the endpoints of the minor axis. Now we need to find the foci. Since we know c squared equals a squared minus b squared, we can write that c squared equals 16 minus 9, which equals 7. Therefore, c equals the square root of 7, and the foci are 0, negative square root of 7, and 0, positive square root of 7. So we have gone through the process of moving from an equation, here, original equation, if you can see it underneath there, putting it in the standard form of an ellipse, finding the vertices that are located on the major axis, finding the endpoints of the minor axis, and then solving for c, which is the distance from the origin, or the center of the ellipse, to each of the foci, located in this case at 0 square root of 7 and 0 negative square root of 7. So again, the steps for graphing an equation of an ellipse is express the equation in standard form, if it's not already there, find the vertices, find the endpoints of the minor axis, find the foci, and sketch the ellipse. But let's look at what happens if we do not start with an equation. What if we start by knowing that the foci of this ellipse are at negative 2, 0 and 2, 0, whereas the vertices are at negative 3, 0 and 3, 0. Notice that both the foci and the vertices only have a non-zero value for their x component. That means the major axis of this ellipse is going to be along the x-axis. And I have placed dots in the appropriate places here for the foci and the axis so that I don't clutter this up. I'm not going to label them directly on the graph. And here is our general form for the equation of an ellipse with its major axis along the x-axis. And here is the equation with the only information we know right now. However, we do know that because of where the foci are located, c equals 2. We also know that c squared equals a squared minus b squared, and if we manipulate this by subtracting c from both sides and adding b to both sides, we get this equation, which we can solve for b. So let's make a little room and record that. So the endpoints of the minor axis are 0 negative square root of 5 and 0 positive square root of 5, as you see them graphed here. And then we can sketch the ellipse. Remember that although the foci define the ellipse, they are not part of the ellipse. The ellipse runs through the vertices and the endpoints of the minor axis. So that is our result if we are just trying to graph the ellipse. But if we want the equation, that would be x squared over the vertices squared. Okay, the distance between the center and a vertex squared, plus the distance, well, plus y squared, over the distance from the center to one of the endpoints squared, equals 1. However, all ellipses are not centered at the origin. We need to expand our understanding of the standard form of the equation for an ellipse. Here is the standard form of the equation for an ellipse that is longer in the horizontal direction than in the vertical direction. The a squared is under the x term. However, that x term is now x minus h, the entire quantity squared, and the y term is now y minus k, the quantity squared. Of course, if this is at the origin, h is 0 and k is 0. And here is the equation of an ellipse that is oriented vertically, where its major axis is vertical. Notice that the h and the k positions did not change. H is still with x and y is still with k, because in each case, the center of this vertex is not at 0, 0, it is at hk. Since my last example was centered or was oriented horizontally, this example will be oriented vertically. You can see here that my h value is 1 and my y value is 3. So the center of this ellipse will be at 1, 3. So 1, 1, 2, 3. There's the center. Looking at the equation, a squared equals 16 and b squared equals 9. So b equals 3 and a equals 4. And those are the distances, in the case of A, from the center to the vertices, and in the case of B, from the center to the endpoints of the minor axis. So I count up 1, 2, 3, 4. Uh-oh, gotta make some room. Okay, there we can place it now, and that's located at 1, 7, 4 units above our center, and 1, 2, 3, 4 units below our center at 1, -1, we have the other vertices. Now we count over 3 units to the right and 3 units to the left of our center to mark the endpoints of the minor axis, and let's label those. There they are, -2, 3, and 4, 3. Then finally we have to find c. Since c squared equals a squared minus b squared, that becomes c squared equals 16 minus 9, which gives us 7, and that gives us c equals the square root of 7. So we have to count up from the center, square root of 7 on the major axis, and down from the center, the distance, square root of 7 on the major axis, to get our foci. And then we can sketch the graph of the ellipse. And that's the end of the new content for this section. And there you have it. Now you know how to graph ellipses when given an equation that graphs an ellipse, how to manipulate it to get all the information you need, or if you are given the foci and or the vertices or the endpoints of the minor axis, how you can find enough information to both graph the ellipse and to generate its equation in standard form. I will also post a worksheet for you in Blackboard with the answers there as well. Please let me know if you have any questions, and I will see you in class.